Hi everyone, today we are going to have a quick introduction into the concept of impedance. It's kind of important in the study of AC circuits because that's the main difference between, that's one of the big differences between direct current and alternate current circuits. In the in a direct current, you just have the resistance of uh, of all the components that's resisting the flow of the current through the circuit. In AC circuits, it's slightly more complicated because apart from resistance offered by the components themselves inside the circuit, you also have a phenomenon called reactance. And resistance and reactance collectively are called impedance. So reactance is the other source of opposition to current flow inside the AC circuit. It comes from two sources. So the capacitors and inductors. Capacitors, of course, even though I'm using the name of capacitors and inductors referring to devices here, but most electrical components, even wires, will have certain capacitive and inductive properties. Yeah, but today we're just going to simplify them into capacitors and inductors. So what happens is as current flowing through capacitors and inductors, they will produce electric field in capacitors and magnetic fields in inductors. And they would interact with the periodically changing current and voltage in an AC system and creating opposition to the flow of current. Yeah. So that's what we're going to looking at today. Of course, the specific details are kind of beyond the high school level course we are doing. So, especially the mathematical components, where a lot of things like complex numbers and phasors are involved. So today we'll just try to focus on making sense of the capacitance and capacitive and inductive reactants in a more intuitive way. Now, let's first have a look at capacitive reactance in a bit more detail. So, if you think about a capacitor, so basically in the idealized form, it's two metal plates between, with a gap in between, usually some kind of insulator or dielectric. Now, as you have a current flowing into the capacitor, one side will be charged up. And I'm just going to use conventional current. So positive, as current flows in, positive gets charged up. What happens is that it will generate electric field that will attract the negative charges from the other side. And the negative charges will build up on this side. Of course, as this side becomes more negative, the whatever's on the other end will be coming across as becoming more positive. So you it will give you the impression that the current is flowing across the capacitor, even though nothing is actually crossing the gap between the two plates. So as the charge builds up, so as this side becomes more and more saturated, things will slow down, and which means there will be less and less. The rate of negative charges will building up on the other side will decrease as well. And eventually, once the positive side becomes completely saturated, then all the possible negative charges will be attached to the other plate, which means there will be no apparent current flowing through on the other side. So for a DC circuit, that's where the story ends. Once the capacitor is fully charged up, then the current flow will stop completely. Now, things gets a bit different in AC circuit. Because in AC circuit, the voltage and current does change over time and the sinusoidal wave in ideal situation. So in this case, the applied current and voltage periodically changes direction. So instead of having the current build up, instead of having the charges build up and saturate the plates and completely stopping the current, the capacitor is constantly charging and discharging. So because as the current flow, charges build up, opposite charge builds up on that side, the current seemingly slows down. But before the plates become saturated and current stops, the polarity changes. So it will switch around, and the current will start flowing in the other direction. So even though as the as the capacitor gets charged up and the current becomes more and more restricted, it doesn't go all the way. So the current can still flow again as soon as the current will continue flowing back and forth as the capacitor charges and discharges. And the way it happens is because let's say this is the voltage. So as soon as the voltage gets lower, so voltage on this side lower, then the current will start flowing. So you actually end up a situation where the current will start flowing the other direction before the charge, before the voltage completely reverses. So you end up in a situation where the current flow will lead the voltage. And if you want to visualize it, as soon as the current, so imagine you start as the plates gets charged up, as the voltage increases, the current flow will decrease until the plates reaches the highest level. But as soon as the voltage start decreasing, the charges built up will start flowing backwards, and you end up with current flowing backwards. So the current flow will end up kind of leading the voltage change by 90 degrees. So with capacitive reactance, we say that in capacitors, we say current leads voltage. This will become important later. Another consequence of this phenomenon is the higher the frequency of the AC source, so the faster the current and the voltage go back and forth, then less time there will be for the charges to build up, and then there will be less restrictions to the current flow. So before the current flow could be slowed down by the buildup of charges, it will change direction. So you actually end up with a reciprocal relationship, an inverse relationship between the reactance and the frequency of the power source. So the formula you actually end up with, reactance expressed as a capital X. So C to indicate it's a capacitive will equal to 1 over 2 pi Fc. So where F is the frequency of the power source, and C is the capacitance of the capacitor. So capacitance is basically the capacitor's ability to store charge. So this is basically a formula we use to work out the capacitive reactance of our capacitor. Alright, now let's have a look at the other source of reactance, which is inductive. In inductor, well, just imagine an inductor. Yep. So as current flows through an inductor, you will generate a magnetic field. Yep. So as the current flows through, if there's a change in current, so usually the case when you switch on the switch, the current increases, then the magnetic field will change along the current. And what happens next is that changes in current, the changing magnetic field will induce an electromotive force in opposition to the current flow. So you end up with, so basically current flows through, as current increases, magnetic field increases, and then this magnetic field induces a electromotive force that's in opposite direction to the current flow. So usually this is called the back EMF because it's in opposition to the current flow. All right. So in a DC circuit, as the current increases, of course, the EMF will oppose and delay the flow of current. But eventually, when the current reaches its maximum level and reaches a steady state, then so will the magnetic field. And once the magnetic field stops changing, then the EMF will decay and eventually disappears. And there will be no more opposition to the flow of current. So that's the property in DC. So as the current flows through, eventually changes in magnetic field stops, so induced EMF stops, which means the inductor would end up acting like just any other conductor. But in the things are slightly different with, well, not slightly, things are a bit different with AC. So in AC, as the current flows through the inductor, magnetic field forms and opposes the current flow, so there is a delay. However, before the current can reaches a maximum level and reach a steady state, the polarity changes. So the voltage gets swapped around. And you end up with the whole thing just turning around. So, in effect, because the current will not reach the maximum possible level, the steady state, before the things are switching around, you end up with current never reaching the same level as it would in a DC circuit. So, in effect, that is that's where the reduction in current flow comes from. And different to a capacitive reactance, what end up happening is the current flow will lag behind the change in voltage. So when the voltage changes, as the voltage decreases, the current flow will increase, and you will end up with a 90-degree delay. So this is in opposite to capacitive reactance, where the current leads the voltage. So in this case, current lags behind. And in the case of AC, if the frequency of the power source increases, so if the back and forth of current and voltage gets more and more frequent, so the time in between each switch gets less, then there's less time for the current to rise before the direction switches. So you end up with the opposite situation to capacitance, where increasing the frequency means more current flow. In here, the reactance, so the opposition to current flow, will increase proportionally to the frequency of the system. So this is expressed by the formula XL, so L for induction for some reason. Yeah. But so XL equals to 2 pi F L for the inductance. So L is the inductance of the inductor. Yeah. So the situation is, higher the frequency, the greater the reactance from the inductor, opposing to the capacitor, where higher the frequency, the lower the impedance. Now, the total reactance of the system, as I mentioned earlier, because the current leads the voltage by 90 degrees in capacitors, while lags behind voltage by 90 degrees in inductors. You end up with a situation where the two reactants actually are 180 degrees out of phase, which makes them acting in opposition to each other. So the total reactance in an AC circuit would end up being X total equals to XL. So the inductive inductive reactance minus the capacitive reactance. So and that's a phenomenon. And of course, do remember earlier we mentioned that there's still resistance in the AC circuit, and the restriction on current flow will be the combined effect of the resistance from the components and the reactance from the capacitors and the inductors. So unfortunately, we will not be able to get into much detail in this presentation because it's kind of more, as I mentioned earlier, it's become a high school level. The ideal situation, the inductance, the reactance and the resistance would act 90 degrees out of phase from each other. So you end up a situation where you can, where the total impedance is expressed as a complex quantity where the reactance forms the imaginary part, so where the resistance forms the real part, and then the reactance forms the imaginary part. But actually, it's it's normally Z, isn't it? So Z. So the impedance would end up with is a complex quantity. But of course, in this course, you don't actually really have to worry about it. What you just need to know is the magnitude of the magnitude of impedance, which is basically because they are 90 degrees to each other. So you can express it via Pythagoras theorem. Wait, sorry. It's the difference between so this is what you really need to know for this course. So in summary, in AC circuitry, we have two sources of opposition to current flow: resistance from the parts and reactance from capacitors are inductors, as the result of the electric field and the magnetic fields interacting with the fluctuating voltage and current. So in capacitive reactance, current leads the voltage, and the reactance is inversely proportional to the frequency. So higher the frequency, the less reactance. And in inductors, the current lags behind the voltage, and the reactance is proportional to the frequency. So higher the frequency, the greater the reactance. And because because one in one situation current leads voltage and other one current follows the voltage, then the capacitive and inductive reactance act in opposite directions. So we end up with the total reactance being the difference of the two. And of course, total impedance, where we just have to focus on the magnitude, which is basically the um, basically the hypotenuse of the resistance and the total impedance. And so there is that.